In this lecture, we are going to study low-pass filter. Here, we'll try to understand what is low-pass filter and how to design a low-pass filter using resistance, inductor, and capacitor. Okay? So let us start this thing. So this is a system. Low-pass filter we can consider as a system, and here we can. So this is suppose one system, and that I'll call it low pass filter. In brief, I'll call it LPF. So system will have one input. This input is Vi, and output, corresponding output, I'll call it V0. Now, low pass filter, basically this term implies that low frequency signal can easily pass through the system. Means low frequency signal, if it is present in input side, that signal can go through the system and it will be available at the output end. Just take one example. Suppose Bi equals to 10 sine 100t. Okay, this is our desired signal. Okay, so I'll call it desired signal, and along with this signal we have one more component that is undesired component, added component, and that is suppose only 0.5 times, right? And I can write it's a cos component or sine component, does not matter, and it is 1000 t. Clear? So we have one signal that is 10 sine 100t, another signal is 0.5 magnitude and cos 1000 t. So for this one, the desired signal, what is the amplitude? So this is called amplitude, this is the amplitude, and this one is the angular frequency. So any signal xt, if it is written a sine omega t, a is called amplitude and omega is called angular frequency. Okay, so this angular frequency omega is related by linear frequency as omega equals to 2 pi f. So this angular frequency, in we can write it is a radian per second. This is the unit, but for linear frequency this unit is hertz. Okay, so in this way we can define the signal in sinusoidal waveform signal. So amplitude and frequency. So suppose this signal is having two frequencies, one is your 100 radian per second and other one is 1000 radian per second. But this only 100 radian per second signal is desired for us. Okay, we wish to eliminate this part, but once it is added, so you will be getting resulting signal. It's not easy to eliminate these things. So we need one system so that to remove this high frequency component. So compared to this 100 radian per second, this 1000 radian per second is comparatively high. So that if we wish to remove it, then we need to use one low pass filter. So here in the output end, we want that only this 10 sine 100t. Okay, the shape. So what is the shape? So can you see the shape resulting one? Okay, so we can draw the resulting signal. Suppose the input signal with respect to time. So this 10 sine 100t, that we can draw. Suppose this is the 10 sine wave. This is your magnitude 10 and this lower side is also minus 10. This signal, green one, I am calling 10 sine 100t. So we can define the t accordingly. this time period. Okay, right. Now over this high frequency component 0.5 cos 1000 t. So this is 10 times more frequency. Means you can see that this green one will repeat one cycle in t second. So in same t second, this second component will repeat 10 times larger. Okay, but its amplitude is only 0.5 and that is added. Okay, so that signal, resulting signal, it may look like this one. So this high frequency component will be added here. So some fluctuations could be there. So I am drawing it roughly. It's not proper. So this undulation is because of this high frequency component. So this one is a resulting one, VI t. Okay, means 10 sin 100 t plus 0.5 cos 1000 t. This addition of these two is this one. But at the output end, we used to get only that component, means this component. Okay, this is the output that we want. So we used to remove this undulation. So that's how we need to use one filter which will remove this high frequency. Undulation means high frequency. Okay, so more variation in short time means higher frequency content. Okay, that thing we need to remove it. That's how we'll go for low pass filter. That is the simple meaning of this low pass filter. So what is the application? We can remove the high frequency component. Basically the noise component is considered as high frequency. If you have some noise added with desired signal, that noise could be removed using low pass filter. We can make the signal very smooth. So one important thing is that low pass filter will make the signal very smooth. So undesired this high variation could be removed and we'll be getting a smooth curve. Okay, very important concept for low pass filter. So low pass filter makes the signal very smooth one. Okay, now how to define this low pass filter? So what we'll do, so if it is a system low pass filter, so it should be defined with by gain. So this output by input will consider one gain. So in Laplace domain, so output Laplace by input Laplace, this ratio is considered as gain of the system, and that generally will call as H of S. Okay, so if you don't know the Laplace transform, no matter at all. So we may discuss later on. Right now you will be able to understand without these things. Just consider that output by input, this ratio is the gain. And now we need to understand the frequency response of the system. So frequency response of the system is given by, so where this H of S is known, there if I replace S by j omega, so omega is the frequency and j is simply square root of -1. It is a complex number. So if I replace S by j omega, we'll be getting H of j omega. Okay, so this is a complex quantity. So this complex quantity will have one magnitude and one phase. That magnitude is, I write mod of H of j omega. This is the magnitude part, and angle H of j omega. So sometimes we write in this form, this is the magnitude m, it is function of omega, and this one we can write in exponential form, e to the power j phi omega, where m of omega is nothing but this same thing. So it's a magnitude part, it's a magnitude of H of j omega, and phi is the angle of this one. So I will define this thing, don't worry. So now we need to design the low pass filter. No? That's how we need to discuss the frequency response of a system. So what do you mean by frequency response? So that we need to understand first. So if I apply, suppose one signal that Vi equals to A sine omega t, then what is the corresponding output? That we want to understand. So if I apply one signal, one pure sinusoidal signal with frequency omega, this is the frequency, then what would be the corresponding output for any system, not only low pass filter? So if it's h of j omega or h of s is provided, so h of j omega or h of s, that will characterize the system. If this is provided, we can find out the corresponding output. So what is the relation? The relation is that this V0 will be, so whatever amplitude was there, the same amplitude, and this magnitude will be multiplied m of omega, and this sinusoidal signal frequency will remain same. It is again sine wave with the same frequency omega t, but this phase, it's again a function of omega, okay, that will be added here. So this is the complete response, okay. So that you need to assume right now here, so we can discuss in other classes how to get these things. But one important thing is that this is the magnitude response of the system that is multiplied with amplitude of the input signal, and the phase will be added. But in filtering, we'll be more concerned about how amplitude is modified. This m of omega is modified. So then we can easily understand what type of filter it is. No? So suppose if I say that, for one example, if I take, okay, just see this one, what I am saying. Suppose if input VIT is 10, we have considered 100T, okay, 100T. So it is passing through that system, and at the output end, we are getting, suppose using this thing, this formulation, it is becoming 8, and it is becoming sine, and 100T, and plus something, suppose pi by 4. This angle is added. Okay, this is for example. So what is the meaning? So amplitude was earlier 10. This is now amplitude is modified to 8. It's a little bit reduced. It is fine. Okay, and this phase pi by 4 is introduced. Okay, now we have another system. The same input is applied. The 10 sine 100t, and this time we are getting, suppose output equals to 0.01 sine 100t minus pi by 6, whatever it is. Okay, so here more important thing is that what is the amplitude, the output signal amplitude, that is 0.01. So it's a very weak signal. So this provides that it is a weak signal, amplitude is very small. So initially the input side, the amplitude was 10, but output side it is becoming very small. So in other words, I can say that this system is not allowing this signal to pass it. Otherwise, here this system will allow this signal 100 radian per signal, because it is almost 10. Okay, so input signal was 10, now it is a little bit reduced, we are getting 8, so that will be happy with that one, right? So in this case, we can say that this system, first system will allow 100 radian per second, whereas second system will not allow 100 radian per second signal. Okay, so it depends on system characteristics, how magnitude pattern is there. So this is the important thing. So that will, by this pattern of M of W, we can define different kind of filters. So in low pass filter, this magnitude pattern should be how it look like. So we can consider this thing. So this is your low pass filter. This is your input signal, Vi. I can write VIS, and output side B0 S, and system transfer function is H of S, and H of S is it is output by input. Okay, so this H of j omega. So here we replace S by j omega. We are getting this H of j omega. So its magnitude, we'll call it m of omega, and angle of H of j omega, that is the phase, we'll call it phi of omega. So we are concerned about the magnitude. So if phase is introduced, little bit positive, negative, doesn't matter. We don't care. Okay, because if magnitude is very small, that means that signal will become very weak at the output end. It is not available. That only we'll say. Okay, that's how magnitude pattern, this m of w, is more important thing. So how will define this low pass filter? So ideal low pass filter will define in this way. So this is the frequency response. You can see that this is the omega, x-axis is omega, and this axis is magnitude m of omega, and the which is nothing but mod of h of j omega. And this pattern, I can say that if it is a low pass filter, then it should have unity gain. No, it should not modify the gain. If m of omega is 1, then whatever amplitude was there input side, output side will be also having the same magnitude, amplitude. No, so if it is flat enough up to certain frequency, so this frequency, suppose I will call it WC sub C, it is called cutoff frequency. We'll define it further. Okay. So here you can see that up to omega c, 0 to omega c, any frequency signal that can easily pass through the system because gain is 1 there. But beyond omega c, it is made 0, means totally absent. Those frequency signal, that amplitude will become 0 perfectly because it is multiplied by 0. Okay, so you understand this thing, no? That already we have discussed, that the output is given by this A. So if input is Vi is A sine omega t, in that case the output will be A into m of omega, and sine will remain sine omega t plus phi. So this m of omega, if is 1, then it will remain A magnitude. But if m of omega is becoming 0, output will become 0. So means that signal will not pass through. That's how we'll call this side as stop band. So beyond omega c, those signal cannot pass through system, but 0 to omega c, that I will call it pass band. This is your ideal low pass filter. It is ideal characteristics. The magnitude should be 1 up to certain frequency omega c. That omega c is called cutoff frequency, and beyond omega c, this magnitude will be 0, and that time those frequencies cannot pass through the system. So that's how we'll call it a low pass filter. Okay, so in low frequency signal can easily pass through system, and high frequency component will be rejected by this filter. That's how it is a low pass filter. Okay, now in practice, how to design a low pass filter using capacitor, inductor, that is the most important part. Okay, so what we will do if we want to design a low pass filter like that? Okay, so before that, what will be the practical magnitude plot that will look like? Okay, may look like, suppose if this is the omega and this one is the ideal plot up to omega c, and beyond that it is 0. This one is h of j omega magnitude, right? So if we go for practical circuit, in that case it may start from 1, okay, but gradually to reduce to be like this, okay. So this kind of pattern sometimes we'll be getting. So if it is better this one, suppose sometimes if we get this kind of plot, obviously this is a better filter. Okay, because it is almost flat after certain point omega c, and beyond that sharply it is reducing and it is going towards 0. Okay, so to get a better filter we need to include more number of energy storing elements. That is important thing. So capacitor, inductor is a must in a circuit. Using only capacitor, inductor we can design filters, but how to use those kind of filters? And here one important thing is that this WC will be called 3 dB cutoff frequency or half power cutoff frequency if the magnitude here is becoming 1 upon square root 2. So the highest magnitude is 1 at omega c. If magnitude falls to 1 upon square root 2, this is called half power cutoff frequency. Okay, or it is also called 3 dB cutoff frequency. So what is the meaning of these two? That also you need to understand. Why it is called 3 dB, why it is called half power. Now 3 dB scale, the gain, this magnitude 1. So we have considered m omega. So if I convert it to in dB scale, so that time we'll consider 20 log base 10 m of omega, that is in decibel, in dB. So if I convert in this way, then we'll get a decibel. Okay, so in this case, so if m of omega is 1, then what is the value? 20 log of 1 base 10, obviously it is 0 dB. So this one, this height we can consider as 0 dB here. So gain 1 means corresponding to 0 dB, and when gain is 1 upon square root 2, that time what is the value? So 20 log base 10 and gain is now 1 upon square root 2. So what is the value here? So this thing we can write 20 log, 20 is multiplied, so 20 log 1, this is division, 1 upon square root 2, so it's log 1 base 10 minus 20 log base 10 square root 2. Is it fine? So you can see this one is 0 because log 1 is 0, minus this square root 2 I can write again 20 log 2 to the power half. So this half will come here, so it will become minus 20 times half times log 2 base 10. So this is 10, cancel out, but log 2, the value of log 2 base 10, its value is 0.3. Okay, so it is 10 into 0.3, it will become minus 3 dB. So this corresponding level I can call it minus 3 dB. So how much it is reduced? It is reduced by margin 3 dB. That's how it is called 3 dB cutoff frequency. Okay, and why it is called half power? Because here gain is 1, here voltage gain, remember voltage gain is 1 upon root 2, so power gain is the square of the voltage gain. Okay, so what is the power gain? Power gain will be at this point will be 1 upon square root 2 square. Okay, suppose in this case here the power is P0. So in this case, what is the power? The power will be that thing. So P0 by 2 square root 2, this is multiplied. So not this thing, P0 into 1 upon square root 2 that square. Because this is a voltage gain, its square will become power gain. So this is the initial power and this is the power gain multiplied, you will be getting current power. So this is square of this one, that's how you will be getting P0 by 2. This power will become the half of that maximum power P0. So at frequency omega c, that's how it is called half power cutoff frequency. Okay, so this is the basic concept of the filter's cutoff frequency. Half power cutoff frequency and 3 dB cutoff frequency, very very important. Now next concern is how to design this kind of low pass filter using RC circuit or RL circuit. So I will quickly discuss this thing. So lots of things are there. Okay, so how will discuss this thing? So one thing, if you have this kind of system, I'll consider one example straight away. This is your resistance, this is a capacitor C, right? This input is Vi, this is the output V0. So if we go for in Laplace domain or exponential input, same thing, okay, but that thing I'll be discussing in other classes. For time being, forget about this one. So if I want to get this V0S or VIS, what this ratio, basically this output by input, sorry, this is Vi, that is your H of S. What I will do, this capacitor, whenever we will find a capacitor, its impedance or reactance will be replaced by this reactance capital X, C, will be 1 upon CES. That's all. Okay. Then you may consider this is one block kind of things. Its reactance, I'll consider 1 upon CES. And if it is inductor, inductance L, then its reactance XL, I'll consider L into S. That's all. So how we are getting that will be discussed later. Okay. So here, if I consider this is resistance R and its reactance 1 upon CS, easily we can use potential divider circuit, right? So this is, we are taking output across the capacitor, its reactance is X 1 upon CS. Okay. So what is output? Can we find output V0S? V0 will be this reactance of the capacitor, that is 1 upon CS, by total reactance or resistances R, this is R, plus this one 1 upon CS. So this fraction will be getting because of potential divider circuit, because we have two elements, we are taking output across capacitor, its reactance is 1 upon CS. So that self resistance or self reactance upon total reactance, okay, multiplied by input voltage. That's all. So this is by potential divider circuit. So what is the ratio? So V0 by Vi, okay, it will give you, so if you simplify it, so I can write 1 upon CS in numerator, here this CS will be here, this is your RCS and this is 1. So this CS will cancel out, so you will be getting 1 upon 1 plus RCS. Okay, so this thing we can rewrite as 1 upon 1 plus S upon omega C, where we can write that where this omega c, what is omega c? It's 1 upon RC. You can see. So this RC I replaced by 1 upon omega c. That's how omega c is reciprocal of RC. Okay. And what is RC? RC is your time constant of the circuit. So if it is first order, so this omega c is becoming a cutoff frequency, and which it is reciprocal of time constant. That is very easy to calculate the cutoff frequency of first order circuit. So what you are getting, this H of S is becoming of this form, 1 upon 1 plus S upon omega c, and I'll show you that this will behave as low pass filter. So we'll try to understand what is the magnitude response for this system, this RC system. Okay. So let us try to draw these things. So what is H of S we have obtained? H of S we have obtained 1 over 1 plus S over omega c. This is the form. So to get magnitude plot or frequency response, we replace S by j omega. So it is H of j omega. S is replaced by, just replace S by j omega, both sides. So left side will become H of j omega, and right side will be 1 over 1 plus j omega, and it is omega c. Okay. So what is the magnitude? So can you now find out? M of omega is the magnitude of H of j omega. What is this? Numerator is real number, so it's 1, remains same. So denominator is a complex number. What is the magnitude of this one? So magnitude of A plus JB. What is the magnitude? Square root this real part square plus imaginary part square. Okay. So here real part is 1. So thus this magnitude will be, this is 1 square plus this imaginary part is omega upon omega c, that square. Okay. This is the magnitude function m of w. Can you draw this thing? Can you see how it look like? We can draw this function m of omega with respect to omega, and omega c is one constant only, omega c, that depends on the r and c. We have seen that omega c equals to 1 over rc. Okay, let us draw the spectral or magnitude plot. Okay, this we want to plot this m of omega with respect to omega. Now can you tell me at omega equal to 0, what is the magnitude? So m of 0, can you see? If you put 0, so you will be getting 1 over square root, this is 1, 1 square is 1, plus this omega is 0 means everything will become 0, this is 0. So 1 over square root 1 plus 0 means it is 1. So 1 by 1 is 1. So meaning is that at omega equal to 0, its magnitude will be 1. It will start from 1. Now can you see at omega equal to infinity? If you go for infinity, omega very large at infinity, what is happening? 1 over square root, this is 1, and this omega infinity square will become infinity, so this is also infinite. So 1 over infinity will become almost 0. Okay. So meaning is that magnitude is going towards 0 for this high frequency. So it is becoming almost 0 here. So gradually you can see that it's monotonically decreasing. As omega is increasing, what is happening? M of omega is continuously decreasing. The shape could be like this. Okay, freely we can draw these things. So this is the plot for m of omega for this RC filter. So you can see that it is not ideal low pass filter, but very close to, somehow it is closer to that kind of shape. thus it's a practical low pass filter. So here you can note that at omega equal to omega c, can you find out what is the magnitude at omega c? So am at omega c, what is the value? So this is 1, numerator is 1, so square root, this part is 1. Now what is this part? Omega c by omega c will cancel, so it will become 1. So 1 square is also 1. So 1 over 1 plus 1 is 2 square root, so it will become 1 over square root 2. So this point, so which point? So this is the point omega c, where magnitude will become 1 over square root 2. That's how this is called 3 dB cutoff frequency. Okay. So simple RC filter will work as low pass filter and cutoff frequency will be 1 over RC. Okay. So we'll conclude this thing, then we'll go for some higher one. So what I am saying that, so if this is resistance and this is one capacitor, this simple system will behave as a low pass filter. If capacitance C, this is resistance R, this system HS we have got of this form 1 over 1 plus S over omega C, where omega C equals to this, that time constant is R into C, so it is 1 over R into C. That is your radian per second. Be careful, okay? This is very simple one. Now similar thing we can design. So this is one R and C. Now similar thing you will be getting with inductor. So if I consider this circuit, one inductor here and one resistance here. Now if I take output from these resistances, this is the output V0, this is inductance L, and this is resistance R, this is your Vi. So how to find out this transfer function H of S, this output by input ratio? So what I will do, I replace this inductor by its reactance L into S, then we will find this H of S. Can you see? It is the output by input. This is a potential divider circuit. So we are taking output across resistance R. So it will be R over total one ALS plus R. Right? It is very simple. Now this thing we can rearrange. You can divide both numerator and denominator by R. So it will become R by R. And this is also ALS plus R by R. So this will become 1. And this will become, we can write ALS by R. And this is becoming 1. So this transfer function is, you can see that again we can write in standard form 1 over 1 plus, this is S up over omega C. So what is omega C? In this case omega C is this one, R over L, or this is actually R over L, or we can write 1 over time constant tau, where tau is your L by R, that is in second. For LC L and resistance LR circuit, the time constant is L by R. Okay, in here time constant is C into R. Here time constant is L by R. Here R is multiplied with C. Here R is divided from L. That is the simple difference. Okay, clear? I hope it is very clear to you. Inductor, and it is also behaving as a low pass filters. Now easily we can understand these things. Okay, which one is low pass filter, which one is high pass filter, how quickly we can check. That is important concept. So what I'll do, I'll give you one shortcut method to identify a low pass filter, high pass filter, band pass filter easily. So you can see that the capacitor, if it is a capacitor, what is the reactance? XC. So X is j omega, I can write, not S. Its magnitude is 1 over omega into C, because 1 over j omega C, that magnitude, S into C. So S is represented by j omega. This is the magnitude reactance. So this is 1 over omega C. Now you can see that when omega equals to tends to 0, that time, what is the XC? XC is becoming infinite. Means, what is the meaning of this? Capacitor will provide infinite impedance with low frequency, close to DC frequency or low frequency. For low frequency, capacitor will provide very high impedance. Okay, that is very, very useful. And if it is high impedance, obviously it will be considered as open circuit. So this one I can consider as open circuit. I can remove it, the capacitor. So whenever low frequency will be there, if you apply low frequency, that time capacitor could be considered as open circuit. So you can remove the capacitor. Whereas, so this is the first clue. And second one is that if omega is close to infinity, is very large, then what is happening? The XC, this magnitude actually, so 1 over infinity will be close to 0. And 0 means what? Very low. So it is a high frequency component that is applied. High frequency. Okay, for that, what is this? Low impedance is offered. And low impedance means if it is close to 0, it is short circuit. So that could be considered as short circuit. So in short, what I am saying that for very low frequency, capacitor will behave as open circuit. For very high frequency, capacitor will behave as short circuit. Okay, this is very useful concept. For inductor, it is just opposite. So we can consider inductor, inductance L. So low frequency, what you will consider? You will consider just opposite, because XL, mod of XL is simply omega into L. So if omega equal to 0, it will be 0. That's how its impedance is 0. It will be considered as short circuit. Whereas for high frequency, this inductor could be considered as open circuit. It's very, very useful concept. So to understand a circuit, whether it is a low pass, high pass, band pass, what I will do, I will try with two signal. One time I will consider a very low frequency signal. I will check whether output is available or not. Okay, like this one. So just check these things. So what I will do, suppose if I want to understand this circuit quickly, this is R and C. So first case, apply DC signal. So it means this is Vi, this is V0. If Vi equals to constants, some A, what is the corresponding output? To get the output, we will replace this capacitor as open circuit. So we will keep this one same as this thing, resistance, but this capacitor will remove it, because we have said that in DC, with DC or low frequency, capacitor could be considered as open circuit. This is open. So if it is A magnitude, it is R, there is no current, it is a 0 ampere current, so no voltage drop across resistance, so this output B0 will be again A. So same voltage we are getting. So whatever voltage we have applied here, we are getting the same voltage, means it is passing through. Means DC can easily pass through. But if you see that if you apply high frequency AC signal, okay, in that case what I will do, capacitor I replace by short circuit. This is shorted. So if it is shorted, whatever input is there, suppose it is A sin omega t, but output will become simply 0. Means this signal cannot pass through the system if omega is high. I am assuming that omega is high. Right? So very high frequency signal cannot pass through the system because capacitor is behaving as short circuit. But for DC signal, capacitor behaving open circuit. That's how we will be getting almost same potential here. So that's how we can conclude that low frequency can pass through, but this is rejected. So low frequency, this is the low frequency, this is the high frequency. So low frequency can pass through, high frequency rejected, thus it is a low pass filter. Very, very useful concept. And same thing you can understand using inductor. Okay, so if you have enjoyed this video so far, can you please press the like button? So we'll be discussing more. Okay. So now, can you see these things? If I consider this is one inductor and resistance, this is input, and this is the output. So for DC, what is happening? And for high frequency AC, what is circuit? Replacement, okay? So in DC, what will do? For DC, inductor is behaving as short circuit. Is it okay? Inductor will behave as short circuit. And it is resistance. This is your VI. VI. So what is the output? Because it is shorted, no voltage drop here. So output is same as VI. So gain equal to 1. Thus, low frequency signal can easily pass through. It can pass through. But what is happening for high frequency signal? For high frequency signal, this inductor will behave as open circuit. So inductor replaced by open circuit. And then it is resistance. So whatever you will apply here, what is the current here? 0 ampere. So what is the voltage here? No current is this side. So output will become 0. Means this high frequency component is rejected. So because of this inductor in series, this high frequency component is rejected, low frequency signal can easily pass through. So this is again low pass filter. Okay, so quickly we can decide whether it is a low pass or high pass filters. And cutoff frequency, I have said that how to find cutoff frequency? Omega c will be 1 over time constant. Remember, it is true if it is a first order low pass filters or first order high pass filter, whatever it is. So cutoff frequency will be true, it will be 1 upon tau for both the cases, low pass and high pass, that we will discuss later on, but this is the case. Okay, so cutoff frequency we can find easily, where tau is simply RC for capacitor, R and C filters, and for R and L filters it is L over R. Okay, I think it is sufficient to find out the exact value everything. Right? Now, if I give you, if I ask you to find out one problem or solve one problem, very easy problem, then we will go for second order, all those things. So this is the circuit. This is R. R equals to, suppose, I can say 100 kilo ohm. Okay, and capacitor is 1 microfarad. Right? Now, if input voltage BIT is suppose 20 sine 10t, what is the corresponding output? Can you find corresponding output? This is the question. So you know that this RC system will behave as a low pass filter, but not only this thing, we want to understand exact value. Okay, so how to calculate this one? So from this input signal, easily you can understand that what is the frequency? Omega equals to 10, because sine omega t, so 10 radian per second. For this circuit, this is the capacitance C. C is 1 microfarad. So what is your H of j omega or H of S? H of S will be, so I can write first time constant. So what is time constant? Tau equal to R into C. Okay, so what is the value? It is 100 into 10 to the power 3, that is in ohm, multiplied by 1 microfarad, means 10 to the power minus 6. So how much you will get? You will be getting 10 to the power. So this 10 to the power 5 and 10 to the power minus 6, so 10 to the power minus 1. Okay, so what is your omega C? Omega C is simply 1 over tau. So this is your 1 upon 10. So this will become 1 by 1 over 10, and that is your 10 radian per second. Is it fine? So for this problem, this omega C is also 10 radian per second. So what is the equation? So H of S is 1 over 1 plus S upon omega C. So I can write this is 1 over 1 plus S by 10. Now we have particular one input. The input is 20 sine 10t. So omega is 10 only. So what is the H of j omega? H of j omega will be 1 over 1 plus j omega by 10. So I need to put omega equal to 10 here, because I need to calculate H of j 10, that is important, j into 10. So what is the magnitude? 1 over 1 plus j, this omega is 10, cutoff is also 10, will cancel out, you will get 1 over 1 plus j. So this thing, its magnitude, so its magnitude 1, what is the magnitude? Is 1 square plus 1 square, square root 2. And what is the phase? This is tan inverse 1 by 1, 45 degree. So this is the denominator, okay. So total phase here, it will be negative 45 degree, I will call it pi by 4. So I have said that this magnitude will be multiplied here with this one, and phase will be added. So what is the output voltage? Now can you tell me the exact output voltage? B naught. So this is 20, and this magnitude is multiplied 1 upon square root 2. Okay, and sine 10t will remain same, and this phase pi by 4 minus pi by 4 is added. That's all. And that you can simplify. It is 10 square root 2 and sine 10t minus pi by 4. So it is a low pass filter, and you can see that its cutoff frequency is only 10 radian per second. It's very low. Okay. Now we can increase or decrease depending on just choosing different values for the capacitor and resistances. Okay. So we can design higher order low pass filters. So I think that we can discuss later, not in the same video. Okay, we can discuss some second order low pass filters by cascading two filters. So in the next video we'll be discussing higher order low pass filters using R, L and C. Okay, so keep watching, and if you enjoyed this video, you can please press the like button. Thank you.